you already know a lot about second-order systems and resonance. In a differential equations class, you learned that if you have a linear differential equation with constant coefficients that has a zero forcing function, so it's a homogeneous equation, that the solutions to that can be written as complex exponentials. So you've already seen that, and almost everything we're going to do builds on that. So there's many, many applications, as we'll talk about. One of them is the mass spring damper system. So if you write a differential equation, you've got the mass times the acceleration of something, d second x with respect to time, and you've got a constant viscous force, which is proportional to the velocity, like friction. And if you've got like a Hooke's law spring constant thing, F equals minus kx, you sum all the forces on that and don't apply anything to it, then this is going to give us the so-called natural response of the system. There's lots of ways of writing these equations. We're just going to remind you that you know about the solutions to this. I don't like this form. It's okay. I would like to divide through by the m. I'll get a slightly varying form of this just because it's convenient. So I'm going to divide out by the m. This will be b over m. This will be dx dt. And this will be k over m times x. This is still equal to 0. The mass is non-zero, so I can just divide by m and get rid of it. So that's a convenient form of doing this. Another form that's convenient to use, just call this some constant a1 dx dt plus a0x, and that's still equal to 0. And I'm going to come up with even yet another form in a minute here. Just different ways of writing this stuff that make more sense in different applications. So if you say, suppose we write x of t as e to the st, where s is just some number and x is our solution. If you take the derivative of this thing, just formally, you get an s that pops out of here, and you take a second derivative of this thing, so you take the derivative of the previous line, it pulls another s squared, another factor of s out there. If we plug each of these things in, for example, into this form, we get this same equation as s squared e to the st for this term plus a1 times s to the first power e to the st, and then we get whatever a0 is times the x function e to the st, and again that's equal to 0. So this is the form, and we notice that we've got the e to the st back in all three terms. It's never 0, it's always positive, so we can just divide through by it, and that gives us this simple algebraic formula, s squared plus a1s plus a0 is equal to 0. So the point is, if we can find roots to this polynomial, we can find the key things that we need for the general solution to this formula, for this differential equation. Now, you can write this in various ways. Let's just notice that for many applications, and most of the ones we'll look at, all the coefficients are not only constants, but they're positive. If that's the case, then it makes it a little bit easier to see what's going on. So roots of the polynomial, there'll be two of them. It's a second order polynomial. And if we use the quadratic formula, and again, I have my own favorite form. I like to take minus the middle term over 2 plus or minus the square root of that same thing, quantity squared, minus this term. That only works because I normalize this guy out. And now this is the form of my equation. Now, that's a perfectly good form. Let me show you another one that may come in handy at some point. And let me see how I want to do this. I will write, I didn't leave myself any room to write this thing. Let me let A1 be omega naught over Q, and we can solve for this. And the thing that was A0 over here, I'm going to call it omega naught squared. So there's just different variables. We can solve for these in all these cases and figure out what A1 is. So let's do it. So A1 was omega naught over Q, and A0 was this guy was omega naught squared. And so in case I need it, I'm going to write this thing another way. So A1 over 2 in here is minus omega naught over 2q. This will be the square root of this thing over 2, quantity squared. So that's omega naught over 2q quantity squared. And this will be minus omega naught squared. Now, if we run it in this form, forgive me for all these forms, I can factor out an omega naught of all this thing. Let me just leave myself some room for it. So this is omega naught, and what was it? I just erased it, so I've lost track of it. And so this term becomes, you can go back and check me, but 4q squared minus, make myself some room over here for writing the general form for this stuff. Now, if, as is the common case, all these coefficients are positive, and if we say, suppose this q is less than a half, in that case, both of these numbers, the two roots S1 and S2, are negative numbers. So they like minus a and minus b would be the roots of these things. All right? If that's the case, which happens for q less than a half with positive coefficients up there, then we can write our solution in a rather general form with a constant here, e to the minus at, plus some other constant, e to the minus bt. All right? Where a and b are positive numbers, these things would just look like, as a function of time, some decaying functions. And the K1 and the K2s are chosen to satisfy initial or boundary conditions, depending on what the problem is. And the A's and the B's depend entirely on the relative sizes of the MBs and Ks, or the A1s and the AT2s, or correspondingly how big this Q is. Again, these negative number roots correspond to Q being less than a half. And that's pretty interesting. The case where Q is equal to a half, we get a different thing. I'm not even going to talk about that. It's pretty boring. The more interesting case is when Q is greater than a half. All right? If Q is greater than a half, I like this formula for this. And what happens is, if Q is greater than a half, that means this denominator gets smaller than one, gets smaller than larger than 1. This number becomes smaller than 1. The argument under the radical becomes negative, and we can factor it out. In which case, we should pull out a j, square root of minus 1, and just flip the sign of this, which I'll just do magically by erasing. And now, this is a thing that we can write in the form of minus alpha plus or minus j omega, where alpha and omega are two positive numbers. And again, we're assuming all the coefficients up there were positive, and this is the case where Q is greater than a half, in which case we get these complex numbers for the roots. All right? We can go back and solve for what these things are. We get that alpha equals omega naught over 2Q, and omega equals the square root of 1 minus 1 over 4Q squared. And in that case, these will be positive numbers. And now the solutions in this case are interesting. We can write the solutions, the rather general solution for x of t in this case, as some constant, I'll just call it c, times e to the alpha t times, and you can write this in different ways. I can write it as, well, let me start out by writing it as, we'll kind of slow down here a little bit. So I'm going to write it as c e to the j omega, I'm getting off track here, e to the minus alpha plus or minus j omega times t. We can factor this a little bit into a form that's got c e to the minus alpha t, which is a damped exponential, times e to the plus or minus j omega t plus a phase constant. If I do that right, we'll talk more about this later, but the most interesting solution, the one that kind of probably provides the most information, is that it's cosine of omega t plus phi. So this says that in the case where Q is greater than a half and all those other conditions happen, we've got two coefficients, C, which is kind of the amplitude of a sine wave at some time, and this is a phase of a sine wave at some time. And this is like, this whole thing is like the amplitude as a function of time. So this one looks sort of like in the time domain, if we just look at x on the vertical axis, we don't know exactly where it is when it starts, but eventually it looks like a decaying exponential, where this thing is e to the minus alpha t, and actually times c, and then this is a sinusoid with a frequency omega, which is all given by the values of the roots. So it's really an interesting scenario, and you've already seen all this stuff, and this turns out to be at the heart of everything we do in so many different fields. In this example, this is the classic mass spring damper system. When we put Q and omega naught and some of these other things in here, these are more familiar with from filters and electrical system theory, but it shows up in many places. And anyway, so what we've done here is reviewed with you the solution to the homogeneous linear differential equation, second order, with constant coefficients. Another time we'll see what happens if this is non-zero. So we get a non-homogeneous equation, and we'll talk about that before long.